Hello, everybody, and welcome back to Business Statistics online at Frederick Community College. In this video, we will talk about Chapter 7, Sampling. And it might feel a little strange that we're jumping from Chapter 1 to Chapter 7 right away. But for this particular textbook, the authors decided to combine sampling methods and sampling distribution in one chapter. That's pretty uncommon. Usually, sampling methods are discussed at the beginning of the course, so don't feel weird about it. That's completely fine. We'll just discuss the first three sections. So why sample? Why do we care about collecting information from a smaller set out of a population? The reason for that is the fact that examining the entire population, which is typically large, is very expensive and time-consuming and actually not needed. Mathematical science is proving that there is a number of objects that needed to be selected from the population that will provide enough information for us to make a very accurate and valid assessment of the entire population. And that's our goal in this class. Look at the population, ask ourselves, what is it that we want to know about this population? Then select a sample from it, compute characteristics of that sample, and that's what we do by computing statistics, and then make an inference or conclusion based on that information about the entire big population. Okay? Keep that goal in mind as you keep learning statistics throughout the entire semester. All right, let's take a look at this quick diagram that gives us an idea what kind of sampling methods we're going to encounter. Now, I also have a more detailed video that goes through all details and several examples of each of the type of the method. So we're not going to spend too much time talking about it in this video. If you need a little bit more additional information, definitely watch that video that's listed on Blackboard. Okay, we have two types of sampling: probability sampling, that includes simple random, systematic, stratified, cluster, and resampling. And then non-probability sampling that just includes a convenience sample. And that's a method that we would use when there's no methodology applied to collecting a sample and we just use information that's readily available. We'll start with the simple random sample. This is a scenario where each member or subject of the population has an equal opportunity to be selected. And Excel uses the sampling method where each subject is put back once it's been selected. So once the value has been picked, it's put back into the population and it can be chosen again. Thus, if you create a sample and you see a bunch of repetitions of the same value, don't be alarmed. That's what Excel is programmed to do. Okay. Now, of course, there is a sampling without replacement, which means the values cannot be put back into the population. They're not returned, and you will have a little bit less repetition with that method. So, Excel can produce a sampling method, a simple random sample. And I have a separate video that goes through all of the details on how to use Excel, which commands to apply to create a simple random sample. Your first assignment, your first weekly Excel assignment will ask you to do a problem of that type. So keep in mind that there is additional instructions that are just associated with Excel functions. Systematic method is the next method that we're going to discuss. This method is applied to samples where each object is very similar to everything else in the sample. So something like quality control. Let's say we would like to investigate quality control of a product at a factory Could be anything. Let's say a computer chip. That's a very popular example. They all look the same. They're all made out of the same materials, right? So it makes sense to just systematically collect a sample where K represents the position of each object in the list. Okay, so let's take a look at the next slide, how we decide what that K is. Here's your formula, and here we start learning a little bit about notation and terminology. Capital N will represent the size of the population. This is the bigger number of the two. And then little n, that's the size of the sample that we would like to collect. So K is chosen by taking big N and divided by little n. And here's a quick example. Let's say we would like to collect a sample of 30, so little n is equal to 30, from a population of size 270. Okay, how would we do that? We would do 270 divided by 30, that would be 9. So imagine the list of your values, and we're going to pick every ninth value. You can imagine doing this by hand, but of course, Excel can do all of these computations and selections for us. And once again, I have a video that describes the procedure in details and shows you how to create a systematic sample. Advantages of this method is that it's really easy to do manually, and of course we typically don't do anything manually. We have software doing stuff for us, and we can avoid bias by not allowing judgments or convenience to affect the sample. There is a disadvantage to this method, and if we have some sort of periodicity in our population, then this could lead to a bias and the sample not being representative of the whole population. Here's a good example describing a situation like this. For example, let's say we're sampling every 8 hours from the beginning and end of a shift. This might not be representative for all of the values during the day. Okay, and that makes sense because if we have a shift starting at 8 in the morning and it ends at 8 at night, there's a variation of all sorts of different characteristic that's happening throughout the shift. So we have to be very mindful how we apply these sampling techniques. Depends on the situation. And I've mentioned this before, and there's a whole science, experiment design, that deals with these kind of questions. How do we select a method? How do we develop a good unbiased experiment dependent on the situation? So keep that in mind. Stratified sampling is the method when we divide the population in mutually exclusive groups or strata. Okay, and then from each strata we select a simple random sample. So imagine your population split into groups and you take a little part from each one of those groups. Okay, again, I have a more visual representation of that in a separate video. If you would like to watch that, I think it will be very helpful. Okay, so here's some examples of strata. At a college, we could have freshman, sophomore, junior, and senior years, right? So you can see there's no overlap. They're all mutually exclusive. You can be one, but not the others. Okay, factory shifts, so first, second, third shifts. Different age categories, so could be something like from 20 to 29, 30 to 39, and so forth. Okay, so this method is applied for which situation? Whenever your population is really diverse, okay, in different categories, and you want to make sure that you cover every possibility as far as the characteristics of your population go. Cluster sampling is the next method. Okay, this one might seem a little bit similar to stratified, but it is different. So cluster involves splitting the population into mutually exclusive groups. and then selecting the entire cluster. So let's say you can split a population in 40 clusters, then randomly select um, 3 of them. Okay, these clusters are often selected based on geography to just kind of help simplify the sampling process. And again, to view a more visual representation of this method, please watch the video that I created separately for this particular topic. Okay, so here are your examples for cluster sampling, individually boxed packages of bulk parts in a large delivery from a supplier. You can see how they're sort of the same, right? So they don't really differ too much, okay? Individual cities where a new product is introduced. Customer accounts balances arranged in clusters by first letter of last name. Okay, so you can think about this concept, something to think about it. How is cluster sampling different from stratified? Okay. Okay, so here's how we're going to explore the differences. Strata are defined with the common characteristics. Okay, so values have something in common, such as students being in a freshman class, right? Strata tend to be homogeneous. Homo mean the same, right? Very similar collection within that strata. Okay. Now, clusters are mini subsets of the larger populations. The clusters look similar among themselves, right? So they tend to be a combination of various characteristics, and they could be representatives of the entire population. Okay, so would we select just the freshman students to represent the population of a college? No, we want to make sure we cover all of the classes, right? Would we select one cluster, one or two cluster? Yes, because they kind of act like mini populations themselves. That's the big difference. Okay, and the last method that we will briefly mention is resampling. That is a method where many samples are just repeatedly taken from the population. We will never do this by hand. We always will use some sort of software, and there's many different softwares out there to produce resampling. Okay, and this method will guarantee a sample, not necessarily guarantee, but it is one way to improve the quality of sample, meaning how representative is it of the entire population. Non-probability sample, okay, so it's a convenience sample that does not have a specific method applied to collecting information. Okay, what are the advantages here? It's quick and easy. It provides general information about the population, but the disadvantage is that it might necessarily be representative of the whole population. Now, when can we use convenience samples? So a good example would be something like a survey for your class, any class at a college, right? Let's say you would like to do a survey about quality of a textbook in a particular class, and then you go out to a cafeteria, collect information from the students that are right there. Okay, is it a representative sample? Maybe, maybe not. But that is what's been done because this is just done for a class project, so the validity of data might not be as important. Now, if it's something like collecting information that will affect the decision that, about big population or big groups, and it's a serious decision, of course, we need to use a little bit more robust methods. Okay, but convenience methods are still used on a daily basis, basically for scenarios where the outcome is not so crucial and cannot be detrimental to the population. All right, so let's jump to the next section, sampling and non-sampling errors. Okay, let me remind you a couple of terms that we've discussed. Parameter is characteristic of your population. right? So something that we would like to know, something that's difficult to compute, something like a mean or a median. Or we can also talk about categorical data. So in this case, we would talk about proportion. Okay, so keep in mind that parameters in general are unknown. Statistics are values calculated from a sample. We've collected a samples, we analyze the data, we can easily compute the mean, median, and many other characteristics of that set of data. These values we will know, we can compute them, and that's what we're going to use to make an inference about the parameters. Okay, and here I'm giving you an example of what a statistic and what a parameter is. Average salary of professors at community college in the state of Maryland is a parameter, and average salary of professors at FCC is a statistic. Okay, is it a good estimate of the parameter? It is hard to tell. We would have to look into more information about the sample that's been collected to answer this question. Okay, so here's a visual representation of sampling and non-sampling errors. Okay, so let's say we have a big population here on the left, and there is a characteristic that we're interested in. We do not know it, right? And we call that parameter. Now on the right, I have my sample. Hopefully it's been selected with a good method, depending on the situation and what we're interested in computing in. Okay, so best case scenario, it's unbiased, simple random sample that's representative of the whole population. We can compute the characteristic, and that's called statistic. Okay, so statistics will vary from sample to sample. And as you guys are going to come up with your first simple random sample on activity number 1, all of you will have different samples. Okay, a sample statistic is not likely to be exactly equal to the population, so we can't expect that, but it will be relatively close. Okay, so sampling error is the difference between the sample statistic and the population parameter. So as you all create your first simple random samples, you're all going to have slightly different sample means. However, they should all be relatively close, and we will investigate the sampling error and see how different methods can affect the sampling error. So this is how we compute the sampling error, and here's a little bit more notation. X bar, that represents the sample mean, that is the value that we can compute, okay, based on the sample that we're going to select. Mu is the population mean. That is the parameter that would like to make an inference about. Now, if we know those two, and a lot of times our population will be finite. So for example, in your activity number 1, you will have a finite population, okay, which means we can compute the population mean. Sampling error is the difference between X bar and mu. And in general, a larger sample size should provide a smaller average sampling error. As we take our sample bigger and bigger, of course, it becomes closer to the actual population. Our sample mean should be closer to the population mean, thus the sampling error should be smaller. But we have to be careful about this because it really depends on which method we use and how our data is analyzed. I'm sorry, not analyzed, organized. How is our data organized? Okay, so the last thing that we're going to discuss is non-sampling errors, and they can occur as a result of questions being ambiguous, okay, a question that lead correspondence to certain values that are desired by the designers of the experiment, and just data collection errors, okay, so these are errors that are not related to sampling variability. As I mentioned before, as we collect a sample and compute statistics from that sample, we expect those values to vary, right? We expect them to be slightly different from the population parameters. And the big question will be how much of a difference is too big for us to start raising questions saying, what's really going on with this sample? Was that a good sample or are there any outliers? And what else could be causing these issues? All right, we're going to go ahead and stop right here. Thank you for watching.